Oh, oh,
And
okay.
I think you will be possible.
Yeah, is it starting recording already?
Did you
Looks right.
start recording?
Yeah,
Yeah,
on
yeah,
our
okay.
side looks like it's recording.
Okay,
Mm-hmm.
okay. Then I will stop. Okay,
Okay,
thanks.
sure, sure. Okay, so yeah. Yeah, so as I was saying, Wayyan, do you want to
Yeah.
share a bit of what?
Yeah. So before you're here, I mentioned that I was actually trying to read up about manifolds, right? This is like the main topic of interest for me. So I tried to learn a bit of differential topology like a few weeks back. Yeah, and I thought it was pretty interesting, right? And I remember I shared a lot of it with Chien Hao, like stuff like what was it? Do you remember what was the stuff I shared with you?
Some local stuff and like
Yeah,
locally
I remember sharing with you something about Brouwer degree, right? Like
yeah, yeah, yeah. Some
some
winding
certain
number.
map, right? Yeah,
Yeah.
something like that, and it was pretty interesting. And then I think it's quite relevant to physics, right?
Mm,
Because
mm,
yeah, so this is something I want to learn in the future as well.
mm,
And
mm,
then at the same time, I'm also trying to pick up some other things as well. Like I'm trying to learn some discrete math as well. This is one area I've been neglecting for a long time. Like it's like one of those like basic topics that aren't super abstract, but it's very concrete and hands-on. So
mm,
now is my time to finally learn this, I guess.
mm, mm.
Yeah, and then
Yeah.
about how I got started with math, right? I remember it is 2021, right? I first started at 20 my passion was first started in 2016, right? Because I got introduced to this whole AI and machine learning stuff, right? And that was my initial motivation. Like I wanted to learn math to be able to do that kind of machine learning stuff. But that this initial goal became like a whole. It just
Mm,
as I learned some math, right, I just discovered like, oh, there's a lot of more stuff out there that's so much more interesting. So I just naturally
mm.
learn more and more math until I completely switched over to the math side by this point already. Yeah, but and regarding the AI machine learning thing, right, it's stats and probability, right? So that's something that I haven't really seriously started learning yet. So I hope to do that one day as well. But I'm actually curious, is anyone here actually interested in this kind of probability stats kind of stuff? Or like
I was actually into computer science last year and the year before, especially AI and machine learning.
Mm.
oh,
So
that's cool. So
I'm
so
also
you
interested.
so I don't know, like can you share some of the work you've done in that?
I did a research. I actually okay. I said like I got into physics again this year. The reason was I did a research, like more like a project on quantum machine learning and probabilistic forecasting using it, and it made me study quantum mechanics again. And while that, I just got into physics again.
Oh, so quantum probabilistic machine learning, it's sort of I'm
Yeah,
assuming it sort of combines both the machine learning part and the quantum physics part, right?
yeah. I did a forecasting on stock time series
Oh,
time series data last year using just classical deep learning models. And actually, what I did was probabilistic forecasting. So this like getting a probabilistic distribution on the prediction. And actually, there were like researches on quantum models of stock market because stock market researchers usually use like stochastic differential equations and like probabilistic tools, and quantum mechanics is also probabilistic in its own. So they kind of used this quantum model. So what I thought was, how about using quantum machine learning for the probabilistic forecasting? Yeah.
Oh, yeah,
Oh,
that's
cool.
neat.
Yeah.
Actually, this is a kind of a this is kind of a different thing, but I recall like searching on Library Genesis one day I found this book called quantum field theory for economics and finance, and that
Yeah.
was like the most bizarre book title I have ever seen. And it turns out
Uh-huh.
that it was essentially about taking this, kind of stochastic, I don't know how to pronounce it, but anyway, those kinds of processes involving like random walks and stuff in finance. They realized that it was very similar to the pass integral in quantum mechanics.
Right.
So they
right.
Wick rotated it and did that, and I was like, this book is crazy, but it's actually really interesting. Yeah.
What I recently thought, the idea I recently thought was like statistical field theories and quantum field theories are all actually effective field theories, right? And maybe since this economic stock market is also very small in its original, but we can't really model it all the microscopic things. So maybe like using effective field theory for stock market or economic market. Yeah,
Wow.
I think that will be quite interesting. So
Oh, so you
it's
could
kind of
do
an
a
idea recently thought.
so you could do a renormalization group for a stock.
Maybe I don't know.
Yeah. I'm like, this is interesting.
Yeah, I remember I was also very mind blown when I was having dinner with a theoretical physicist, and he told me that about how QFT is actually used in stock market analysis, and I was just like, huh, what? It seemed like two completely different, but yeah, we get that kind of amazing relations at a cool.
Yeah, actually, I think like Wilsonian renormalization is, in fact, like a very versatile idea. So the basic idea is, you want to define like a sum over functions, but you can't do that because functions are not discrete variables. So you cheat and say that functions are discrete variables by creating this kind of lattice with size A. And you realize that obviously it depends on the lattice size. So you decide to, we'll just change the lattice size and see how things change. That is essentially the idea of the Wilsonian renormalization group. And I think it's actually a very versatile idea. So you could apply it almost anywhere in the case where you have like functional, distributions and stuff like that. So I think this could be used a lot.
Well, I just found the book, that Jiwoo mentioned. This is I just found the online bookstore market, which is selling Korean online bookstore market, which is selling the book. And,
Wow, it's very expensive.
Yeah, it's,
I actually have a PDF version of this. And
Oh, yeah,
it
yeah,
is
me
really
too.
interesting. Yeah.
Yeah. Quite the book, yes.
Mm.
And it's selling for about $300. Wow.
Wow.
books are so expensive, but I heard that in Korea, the United States book are really, really expensive. Like not the international edition, but the United States book are really expensive. I heard that because of the companies, like publishing companies.
Yeah, the books are super expensive. So nowadays I just download the PDF and then get some printing company to just print out the entire book on paper. I think it's far more convenient that way. Rather than having the actual hardcover. Yeah.
Just in case you guys didn't know, I'm not sure if I should probably say this and put it on my YouTube, but I use a website called LibGen. Have you guys heard of it?
I wish
LibGen is so popular.
I'm sure everyone has heard of that.
Okay. So I just did a quick search, and the QFT for finance and econs, it is there on there. So yeah, because you guys are talking about the price, I just thought that in case you guys didn't know, you guys can can
Also Sci-Hub.
Yes.
Okay, cool. How about Ariana, Alex, do you want to share a bit about yourself? Sorry.
I want to say one more thing. And
Okay, sure.
if you want to read a article, but sometimes you need to pay for the papers, right? And in that case, I think I can give you help because I'm a university and graduate student, and
yes,
access to the all kind of papers via the university. So if you ask me, then I can download the papers. I can download the papers and give back to you.
Oh, okay. Thank you. Thank
Oh,
you.
that's cool.
Great. Yeah.
Wait, do you
I
guys
think
know?
I might have one paper in particular that I want. It's like I wanted it since like a very long time ago, but now that you mention it, I remember it. Yeah, you can.
Wait,
I'll send you later on. You can continue.
are you guys aware of Science Hub also? Science, SC.
Yeah.
Yes.
Yeah.
Sci-Hub.
Yeah.
Yeah. So
Yeah.
for that works for papers. So it's also kind of based on LibGen. I heard.
But
Mm.
sometimes I does not
Yeah.
work for
Right.
Oh,
some cases.
I see. I see.
Mm.
Perhaps for the newer
Summary.
papers, perhaps. Yeah. Okay. Cool. So yeah, I'm not sure if Ariana spoke before I came. Sorry, I'm late. But Alex, do you want to share a bit about your interests?
Sure. Yeah. I think I'll be a bit more specific this time. Nowadays I'm mainly working in mainly studying algebraic geometry, more specifically currently elliptic curves and isogenies, but slowly going towards higher genus surfaces kind of stuff. Because I have an attachment with someone later this year,
Oh,
which
cool.
will be doing some genus 2 or higher genus for attacks on Jacobian stuff.
Oh wow, cool. Wait,
Yeah.
who are you attaching with? Is it from a local uni?
It's from DSO.
Oh,
You
cool.
can
Wait,
search out Yan 40.
what's the name?
Yan 40.
Yan 40.
Yes.
FOTI
just
or
BOTI.
oh, wait, I didn't know DSO does.
Yeah.
Oh, I
They
see.
invited me here. Then,
I
you can
I
see one of the papers here. Pretty nice
Oh,
stuff.
cool. I see. Is the person is a specialist in crypto, right? So I see.
Yeah.
Oh, so is your research more of math for crypto?
Yeah, it's more of crypto than
Ah.
other stuff.
Oh, that's really cool. Cool.
Yeah.
Oh yeah.
As a matter of fact, now that you've mentioned algebraic geometry, which I don't know much about, but I have a friend who is very well versed in these topics. In fact, he took on the kind of difficult task of doing research alone on the Langlands correspondence this year.
Oh
He,
wow.
yeah, he is an insanely interesting fellow. He was actually in IMO last year and this year. His name is Unsu Herb. I'll write it in the chat. I'm not sure if he's in the WhatsApp room, but I could get him to contact with you if you have any ways of contact. I mean, because he is really interested in algebraic geometry.
This is difficult.
Wow. The paper contains lots of numbers, very huge numbers.
That's really cool.
Recently, one of my friends asked me about about the perturbation theory in perturbation expansion of Hubbard models, and
Hmm.
wait a minute. And there was a fraction oh, I think I should share the screen. Can you enable the sharing the screen?
Oh, okay, sure. Enable. Sure. You should be able to now.
Okay. There was a fraction like this.
Oh. Right.
So you can't rationalize it anymore, right?
I think so.
Wow.
Yeah.
Kind of reminds me of the monster group, like huge numbers that come out of nowhere.
Then there was someone doing research in some, I think it was modular forms, and then when he did the expansion of one of those polynomials, the number turns out to be a number that appears +1, and then this coincidence led them to do a bit more digging, and I think they found out some relation between between two very different fields of math. Yeah.
Oh yeah, that's interesting.
I think it's the field of study
The
is
monstrous
called
moonshine.
yeah, monstrous moonshine and vertex operator algebras. So I'll just type that in chat.
Yeah, about large fractional numbers, there's this very nice problem which is consider a right angle triangle where each side is rational. And does there exist some right angle triangle where side lengths are rational and the area is like 157 or something? So that's how I can solve it, assuming the Bird-Singleton die conjecture.
Oh. Oh yeah, here's a fun fact that I guess I'll share about Alex. Since he didn't share it himself. I think Alex was he wrote some stuff on Twitter, right? And then there was there was someone who offered him a PhD position in something like crypto, right?
Wow.
Yeah, so Alex actually got offered his PhD at age 18. Crazy. Yeah, all right. Sorry, has Jin Yin spoken? Are you there? If you're there, do you want to?
As a matter of fact, Jung-in would kind of like to, participate as a listener for this talk. He told me that he would be more of a I should say this, more of a spectator, which is
Oh,
totally
okay.
fine. Yes.
Sure. Yeah.
Okay.
Okay. Perhaps Jiwoo, do you want to share a bit? Have you shared about your research yet?
Oh yeah, sure. Just a second. I have something that I need to check. Wait,
Okay, sure.
just for about a minute or so.
Okay. We'll continue. Let's chatting informal. For I'm curious. Sunwoo, you're in university now, right?
Me?
Yeah.
No, I'm with the same high school with Jiwoo.
Oh, I see. So you're 18 years old too.
Oh,
How
pardon.
old are you?
I'm actually 20 because
Oh.
no, it's 19 for the international age.
Oh.
18. The birthday is coming this September.
Oh, cool. Happy birthday.
That's because like I just took off the school for 1 year or so. Yeah.
I see. Is your interest also in theoretical physics, or is it in more general physics?
I actually have very broad interests, so I'm also interested in computer science and physics and yeah. So
that's good. Okay, cool.
currently I'm kind of into physics right now, physics and so I'm studying quantum fields recently and geometries.
When you're into CS, what area of CS were you into? Were you into the informatics Olympiad, or were you into machine learning?
No. Just study by myself, and I
Oh.
did AI and machine learning rather than this problem solving algorithm. Yeah, I'm not really an expert on that.
Oh, okay. Oh yeah. Since you're a bit into AI, maybe I share this channel. It's called 2 Minute Papers. It's a YouTube channel, and he summarizes recent developments in AI in a very concise and interesting manner. So you might be interested. Yeah. Okay.
Nowadays, AI is a really a big market, really big market, and I think I heard that the competition is really hard. Competition is really like they're very hot, and the new papers come out every week like that, and new papers come out every week, and they have to read all the new papers, and only one of them survives, and it produces another new papers, and one of them survives, and go on and go on and go on. Like I heard that AI the research is going like these things like this.
Oh. Yeah. I suppose with the amount of applications you can bring, there's a lot of people funding AI research. So Yeah, that's
And
not necessarily a bad thing also.
there is a, and someone says, and there is a someone says that if you use the word machine learning or AI in your research proposals,
Mhm.
then it enhances the probability of acceptance like that.
Oh yes.
Yeah.
Yes. When you yes, because you get grants from people who are not experts in the
Mhm.
field.
Yes,
Mhm.
And the fourth industrial revolution is all about AI, so of course.
yes.
Yeah.
But sadly, I'm not interested in AI.
Well, maybe if you do the experimental like scanning tunneling microscopy, right? Maybe when you analyze the data, if you use a bit of linear regression, you can just throw in the word AI.
Well,
Yeah.
I use the actually I use some feelings to analyze my computational
Mm,
outcomes. And
mm,
yes, that consider, and it's non-linear fitting. Then it's an
mm.
AI.
Yeah.
This machine learning story kind of came up. Like there are researches on using AI on quantum antibodies and things like that.
Oh yeah.
Yeah.
So
Mhm.
there are very interesting quantum machine learning projects and researches.
Mm, mm.
And
Recently, there one of the professors in Seoul National University, the Department of Material Science and Engineering, he researches about like generating machine learning molecular dynamic potentials using density functional theory.
Oh.
Like molecular dynamics is a classical dynamics using some modeled potential between molecules, like the Maynard-Jones potential or other things. But
Mm.
he is trying to generate these potentials using machine learning from the data set obtained from density functional theory. Yeah, those kinds of research is also going
Mhm.
on.
Mm, mm. There's also people using machine learning to find like superconductors and
Yes, yes.
And there's also like I don't know much about that field, but there's like this field in quantum gravity where they do ADS-CFT related to like quantum computation, which
yeah,
is a whole nother thing.
oh wow.
Yeah, yes, weird. I'm not exactly sure what they do, but it seems like they have this discretization of ADS-CFT, which is done with quantum circuits or whatever. It seems interesting but difficult.
I think it was a video about quantum information. Like so
Oh yes, yeah, quantum information.
so in quantum computation, like when making devices, there are very lots of decoherence and noise. So they try to reduce the errors from quantum computation, and
Hmm.
I think it was like about yeah, trying to conceal the information of the system, like yeah, something like that.
Huh, that's interesting. So there's like a lot of von Neumann entropy going on,
Yeah.
which is actually I don't know much about quantum computation, but I am really somewhat interested into entanglement entropy. So like
Mm.
yeah, entanglement entropy is like super cool because of like the Ryu-Takayanagi formula, which says that if you have entanglement entropy on a conformal field theory, then there is this dual gravity theory where the amount of the entanglement entropy is equal to the least area surface that the area of the least area surface that goes into this dual gravitational manifold. So yeah, that
Oh,
was
oh.
super cool. Yeah.
Okay, I don't really I don't know enough to understand what you just said, but something you said about least area surface,
Yeah.
does your work have anything to do with minimal surfaces?
Oh yeah. Yeah. It's kind of like it comes from like the minimization of the action.
Mm,
Like
mm,
you can actually prove this Ryu-Takayanagi conjecture thing
mm.
fairly easily. Using the replica trick. And basically, it all amounts to doing a saddle point approximation of the gravitational action, the gravitational path integral, which basically means that you want to minimize the Einstein-Hilbert action. But when calculating this replica trick geometry, you end up with a geometry that is basically normal ADS space all over it, but it has this surface where it has a deficit angle, which is basically going around a line in a going around a point in a two-dimensional plane, and you go around more or less than 2 pi degrees, and you end up at the same point. So it's kind of like the surface of a cone. But as you can understand using physical intuition, the curvature, the Ricci curvature, the Ricci scalar on a cone is a delta function on the tip of the cone. So you get the idea that this Einstein-Hilbert action, which is the Ricci scalar integrated over the manifold, will be equal to, due to the delta function, the total area of the deficit angle. And you minimize that because you have to minimize the action. So it really comes from there. Yes, it's actually deceptively easy, which is if you assume that, if you just take ADS-CFT as granted, which is not a good assumption because knowing why ADS-CFT holds is like really difficult, and I know nothing about that. But just assuming that it holds, you can derive it really easily.
Oh, cool.
I actually can find the paper which has the derivation in it. Let me just see.
So maybe I don't fully understand, but are you saying that if you use ADS-CFT as a tool, you can prove the Ryu-Takayanagi conjecture really easily? Or
yeah, it's called in my opinion, it's called a conjecture because the ADS-CFT is a conjecture. So it kind of piggybacks on the conjectureness of the ADS-CFT.
I see. Oh, okay.
It's actually really doable. In fact, I'm going to paste the archive link into the chat right now.
Okay, cool. Thanks. Wait, then if ADS-CFT, the conjecture, if it doesn't hold, then does that mean that the proof also doesn't really hold?
Yeah, but I don't think that anybody would seriously think that ADS-CFT doesn't hold. I guess it's like a really well-held belief with many examples shown to be true.
Sort of like the Riemann hypothesis, or? Okay, I'm not very sure. I could be talking about it.
Actually, I'm not sure either. I'm not entirely sure what a conjecture means in like the area of theoretical physics, because the terminology is kind of different. There is this meme that proof in theoretical physics means sketch of a proof in mathematics. So like,
I know that. I know that meme. I have the picture of the table, but yes.
Yeah.
May I?
Jiwoo, because I don't really understand ADS-CFT, but now that you say it's a conjecture, could you? I thought it's a ADS-CFT is a duality that has been found, or is it still a conjecture, or somewhere in between?
I would say that it is very strongly motivated in the sense that I'm not sure if it's so like if we have this.
What are the parts that have been proven, and what are the parts that have remained a conjecture?
I'm not an expert on that part, but specific examples for proofs for specific examples of ADS-CFT do exist based on what I know.
I see.
But the overall idea is kind of very strongly motivated by very convincing arguments. So it's not at the level of conjecture as an ER equals EPR conjecture, which is more of a vague idea and not concrete, whereas ADS-CFT is a reasonably concrete idea which many people are doing research based on. And there are like explicit dictionaries from the ADS side and the CFT side that are very strongly motivated. So I would say that, yes.
I see. They're still building the complete picture, I guess. Cool.
Yes, but it's pretty usable even at this point. Like, but I don't really know much about this at the research level.
I see. Cool. Okay.
I kind of wanted to study the holographic correspondence recently, and I'm not really the level for that, but I just searched for that in YouTube, and there was actually an MIT lecture on string theory, which also covers ADS CFT, and the prerequisites were just relativistic quantum fields. So maybe if you're interested, you can go forward the video.
Okay, sure. That sounds interesting. So it's by MIT.
MIT string theory.
String theory.
Maybe it'll come up if you put on the link.
Oh, is it the string theory and holographic duality?
Yeah, right.
The 8.821. Okay, cool. That's cool. Yeah. How about we transition to the Jiwoo, do you want to present anything, any slide or?
Well, right now I'm just thinking of first like just doing a personal introduction, if that will be okay.
Sure. Yeah. Anything. Yeah.
Yeah. So I would say that I am mostly interested in finding a quantum theory of gravity. So I want to be a theoretical physicist and I want to do high energy physics, but the question that motivates me the most is what quantum system is space-time? Because this space-time is very weird. Like it's not like in quantum field theory, you can quantize a field on space-time because that has been very well set up. The thing about general relativity is that it's background independent. So it's no longer really about a field functional, and thinking of it as a field functional is kind of detrimental from a geometry point of view. These days, I'm interested in topology change in quantum gravity, which basically means that in the spirit of the Feynman path integral, you would have to sum over various possible geometries of the universe. And in a simple model, you would only sum over like the geometries that have the same topology. But now in a recent paper, there was this result that showed that if you want to have information conserved in the evaporation process of black holes, which is essentially the black hole information paradox, you need to consider geometries with different topologies. So what this means is that the topology of space can quantum fluctuate into like different topologies, and you could have a wormhole forming due to quantum uncertainty and stuff like that. And this kind of strays even further away from the quantization procedure of quantum field theory, because now it's really not about fields. It's about wormholes forming, and how to quantize that is like a really conceptually difficult question. And I'm trying to approach that step by step. And right now I have done some calculations on some very simplistic models that are first, the action is a topological invariant. So you can think of it as the topology being decoupled from the geometry, the lengths and stuff like that, the topology being decoupled from the metric. And even there, I made things easier by not thinking of wormholes that travel through time. So under all these assumptions, I got a toy model that was kind of solvable, but I also had to do some other weird assumptions to get it to work. And right now, this is kind of confidential, so you could just remove this.
Okay, wait, hold on. Let me just pause the recording.
I'm sorry, but I'm really not familiar with the idea of topology of spacetime. So wormholes are wormholes considered as like singularity of the space, or
well, spacetime is basically a manifold, which is pretty much in layman's terms like a curved surface. But like if our space time was shaped like say a sphere, as in a 2D surface, a spherical surface, a wormhole would be like changing that into a torus. Yeah, so it's that type of thing. So these geometries are all included in a giant path integral over all possible geometries, which is by no means mathematically rigorously defined, but we could try.
I guess I have a question about how you got started into all these, because personally for me, I started in quantum mechanics, right? Schrodinger's equation, then quantum field theory, and now I'm doing a bit of condensed matter. But for you, what's your journey in being interested to now doing quantum gravity? Because throughout throughout my studying, I've never really naturally went on to studying topics like that. So how do
Oh
you
yeah.
like enter this field, you know? What books do you follow, or
Well,
do you have a mentor, or
oh yes. I actually had, there's these classes where postdocs from foreign universities come to visit, and this person called Sean Weinberg came to our school to talk about quantum mechanics and quantum computing.
mm,
But on the last day, he talked about ADS-CFT,
mm,
and that was interesting. But I guess at that point I wasn't really well versed in things like quantum field theory. So studying quantum field theory was the first thing to do.
mm,
But nowadays, at the start of this year, I had this person called Junhee Kim who participated in the IPHO in India 2015, and he did a series of talks, and he actually chatted with me a lot, and I realized that uh, in physics, like a really new and refreshing idea can be an idea can be new and refreshing, but at the same time not have that many prerequisites. Like the
mm.
idea of
Oh,
non-commutative geometry does not require any prerequisites. Like you only need
oh,
to know the idea of a representation of a geometry, and you just have to make the ridiculous statement, what if x and y do not commute? So
oh,
like uh, of course you would need to know a specific set of prerequisites to kind of do research in like things like quantum gravity. But while you are on the way to studying quantum gravity, you will most definitely meet like a lot of questions. And as you delve into answering these questions, you would end up with weird things that didn't come up before, perhaps
oh,
like probabilistically. And kind of going deeper into these personal questions could get you somewhere, was the kind
oh,
of mantra that I had for myself this
oh,
year.
that's cool. Okay. If you were to, let's say, guide someone, like let's say me, into your field, what books would you recommend, or what resources, any lectures, YouTube
Oh,
lectures?
I would personally recommend for simply general relativity and quantum field theory, the books by Anthony Z.
Mm-mm. Yeah,
I really like those books.
I see.
But like as a basic, not basic, but like as a kind of a dictionary and a reference guide to relativity, I think nothing really beats the
Mm,
level of Wald's general relativity, although it is painstakingly rigorous in some points. So
mm,
like Wald's relativity is a good like book to keep on your bookshelf. And in the quantum gravity part, there's actually a very good introduction to quantum gravity that skips a lot of details, but is still very informative by Professor Hartman. And
mm, mm.
I've given you the link before, but it's
Yeah,
actually really good. So I'll paste it in the chat once again because
okay, sure, sure. That's cool, that's cool.
it's actually really neat. And yes, so I guess yeah. And since quantum gravity, there's nothing really finalized, and you can't really. There's no single satisfactory quantum theory of quantum gravity right now. I guess it's really about just studying whatever you want to study and trying
Mm,
to think of what fresh ideas you would think up when you become like a graduate student or something.
mm, mm.
I
Okay.
don't really know because I'm just starting in this field anyway. So
Mm, cool,
I just
cool.
found the article, paper with a very interesting title.
Mm,
yes.
mm-hmm.
This work is entitled Graphene Wormholes, a condensed matter illustration of Dirac fermions in curved space.
Huh?
Wow.
Dirac
Graphene
from there?
wormholes. Uh, they are they are talking about two graphene sheets connected by a carbon nanotube.
Two conducting sheets, is it?
Two graphene sheets.
Oh, graphene sheets.
sheet.
Right. Oh,
Oh,
okay. So
okay.
it's like a wormhole for electrons,
I yes maybe.
maybe.
Yeah.
Oh, okay. This is really cool, actually. Like,
Mm,
wow.
There are some condensed matter physics experiments or theories, like analogous to the relativity phenomenon
Yeah.
mm.
theories.
Oh, and there's some,
I think it's very interesting.
yeah, and there's some condensed matter systems. I mean, my mentor once said that condensed matter physics is interesting because every material is like a different universe. So there are a lot of like a lot of analogs that you can find in condensed matter theories, like for Majorana fermions or axions, and so that's something that condensed matter physics offers.
I heard that one of a few years ago, a paper published in Nature argued that they found the Majorana fermion in condensed matter, but later I don't know the right word. It disappeared from the Nature journal.
Oh yeah, I know that.
Yeah.
It was like a really terrible incident. They did not keep their scientific integrity. Is that correct?
I don't know the exact behind story, but I think it after the post publication reviews, I think it was considered to be false, maybe.
Yeah. I've actually read a few like articles on that particular event, and it turns out that it was a bit of a like an intellectual scam of sorts. Like, you should always keep your scientific. Excuse me. Yes.
Was it an experimental paper? Experimental physics or?
Actually, I think it was. Yes.
Mm-hmm.
I guess experiments are like, if you're not honest about your experiment results, then that's not good at all. Like, you could get in big trouble, and I think that's what happened.
Oh, I see.
Yeah, it was it is they said in this letter we reported electrical measurements and numerical simulations of high blah blah blah.
I see, I see. Oh yeah, that's also one thing that theoretical physics has, I guess, that in theoretical physics there's nothing to, in a sense, fake, because all the calculations are mathematical. I could be wrong, but at most you can get the calculations wrong, as in there won't be fraudulent data, I guess. Same for math.
Yeah, but there could be still like in theoretical physics, a lot of the mathematical results can be interpreted a bit differently, and you might be interpreting your results too generously. I think that could be something that's happening.
Yeah. Okay, that's cool. Would you guys like to hear about what I'm working on?
Yeah, I'd love to.
Of course.
Sure. So I think I can share a screen. This is okay. So are you able to see this PowerPoint slides?
Yes.
Yeah. Okay. I won't go to you guys can stop me at any time to ask questions. So I do research mainly in topological physics. So it has many interesting applications and stuff. And it can range from the simple stuff like maybe like in condensed matter physics, some simple ideas, to things like string theory, where they consider compactifications and way more advanced stuff that I don't know at all. But specifically, I deal with something called Berry curvature. So as you know, that if you have a sphere, you can parallel transport a vector in a circle, in a loop, and when you return, it has rotated, right? So this is known as holonomy, and this is a mathematical term, meaning that in math there's some connection, right? And you get you get the metric, and then you get, I think it's Christoffel symbols, and then you can write this all mathematically in a rigorous way. Yeah, but so the point is that when you go a loop, right, you can get a certain rotation, and so in quantum states, when you parallel transport it in a loop, you get something, you get a phase which is called a Berry phase. So this also has connections to I think it's the U1 gauge field or something, but the math I'm not too sure, but there's something about U1 gauge connection 1 form, stuff like that. So the Berry phase is yeah, you get a Berry phase, and if you shrink it down to a very small loop, you get a Berry curvature, which is a curvature 2 form. So the Berry curvature is the curvature 2 form on some connection. And so one realization of this is in condensed matter system. So if you have a Berry curvature F, in a 2D, so you have a Berry curvature F, which is a curvature 2 form, right? So the curvature 2 form depends on dimensions of the manifold. So in 2D lattices, right, this is condensed matter system where you have ions, and then you have hoppings from one ion to the other. So you apply Bloch's theorem to turn into momentum space, and momentum space is then periodic in 2 pi. So your quantum states are labeled by quantum numbers kx and ky, and these are periodic by 2 pi. So the parameter space that describes these quantum states is the donut, it's a 2 torus. So if you consider the curvature 2 form on this torus, and you integrate it over the entire torus, you get something called a Chern number. And this Chern number, there's some, it also appears in math, and yeah, it's something called Chern class, and it's all in the study of in the study of, I think it might have to do with
Homology.
yeah, homology. And I'm not very, honestly, I don't know the details, but yeah, it's just a very rich area of math also that people study by itself. And in fact, that's the area of math that can find its application in physics in these condensed matter systems, resulting in things like the tenfold symmetry of formation models. So anyway, also my research focuses on this Berry curvature part, and namely for certain Hamiltonians, for certain 3x3 models, it turns out the graph of Berry curvature, so this is a Berry curvature graph, the x-axis is kx and the y-axis is ky. So you can see this graph is relatively uniform. So my mentor found these uniform models, and my goal was to show was to try to understand why these models can be quite uniform. So there's quite a niche field called the Majorana stellar representation, and basically is decomposing quantum states into spin half systems. So for example, the spin half system is a C2, right? And then you quotient out with the phase U1, is equivalence ratio they quotient out by, and in the end the space of spin half quantum states is complex projective 1, CP1 space, and that it turns out CP1 is isomorphic to the S2, the sphere. So basically all spin half systems can be represented as a point on the sphere. And so one question to ask is, what does this offer besides saying it's a point on a sphere? So it turns out that this is good because the Berry curvature is the Berry curvature of spin half systems is actually the solid angle on the sphere. So there's a very nice geometrical picture. So that's where the geometry part of this topological physics comes in. So yeah, so there's a, if you see it is, here the Berry curvature is a solid angle. So that's what the block sphere representation offers. And so one question to ask is, if this is available for spin half, how about things like spin 1? So for spin 1 models, it turns out there's no block sphere, but it's actually 2 block spheres. So if you have a spin 1 system, it becomes 2 spin half systems. If you have a spin 3/2 system, then it becomes three block spheres. And there's some entanglement as well. But this thing is called Majorana stellar representation, and I haven't really seen it in undergraduate physics textbooks before. So I think it's quite a unique niche field that that's why I'm also able to do this project, because there's not that much prerequisites. So I have a video on it if you are keen, where I explain it in detail. There's some bosonic algebras to deal with. So basically I write the Berry curvature of 3-band models in terms of the 2 Majorana stars, and I came up with this formula. Essentially, this is the main result, and plotting. So I said that the Berry curvature can be expressed as 4 different sum of 4 terms. So the 4 terms are in terms of 1 star, the other star, and some mixed terms. And turns out there's some divergences when we plot these. And why that's interesting is because when we have divergence, then that means that when we add up a few terms, right? You see that T1, T2, and T3 all have divergence, but when you add them all up, the divergence disappears, so they must cancel perfectly. So I understood why they cancel well, and this is work that is done at the end of the year last year, but recently I worked to generalize this a bit to understand more types of divergences. So one thing that might be interesting is something called accessional points. I'm not sure if you guys have heard of it before, but if you know complex analysis, you know that there's under the square root, there's some branch points, right? And these branch points, when you circle the branch points, you get interesting switching behavior. So it turns out that in condensed matter physics and in things like optics, right, there's these accessional points in physics as well, and they are studied under non-Hermitian systems. So I'll just type that in the chat. So non-Hermitian systems is also something that is relatively new in physics research in condensed matter and stuff. And because of non-Hermitian systems, you get accessional points, and this gives rise to, I guess you can sort of feel the topology, aspects of topology coming out, where you have winding numbers, maybe homotopes. Yeah, but I don't know a lot of the details. I'm just trying to work to publish my paper around this sometime this year, hopefully. Yeah, so after that I'm actually keen in doing more research in higher energy physics. Like I want to understand conformal field theory.
Oh, yeah.
Yeah, and hopefully after that I can understand aspects of things like ADS, CFT. But right now I'm just focusing on these projects. Yeah, so yeah, that's all. So
We
if
should
you guys,
like write a paper together sometime. Like that would be super cool.
Sure. Right now I think right now our understandings are like quite disjoint, perhaps. I don't really understand anything you're doing, but hopefully next time when I work towards conformal field theory, and we can meet somewhere and work on the paper. That'd be cool.
Yeah, it could be like our second paper. Like
Yeah.
I also like want to publish a paper this year, but for me it can be difficult because my current advisor is, I checked, and my current advisor is not an archive endorser.
Oh, I see.
So that is an issue, and so I'm trying to. I guess I could kind of find someone who can endorse my paper after I write it, but like I was wondering if you have any tips about that. Like for you, for example, you were able to like just contact a professor at a local university. Is that correct?
Yeah, that's correct.
So like, how do you like contact professors?
Okay. Wait, I'm curious. Your mentor does not endorse archive, meaning that he does not want to publish on archive, or so?
He has many archive publications, but before 5 years ago. So like that's the difficult part.
Now he only publishes in journals?
No, the thing is he hasn't published papers during the last 5 years, which is somewhat difficult, because then you can't be an endorser on archive if you haven't published for 5 years.
So the archive system is there's actually an endorser system?
Yes,
I was not aware. Okay.
To upload like your first paper, you need to be endorsed by someone who is well versed in the field.
Oh, I see. I thought anyone could just submit stuff. I see, I see. Okay. Okay. So personally, for me, I when you want to meet new people, I guess you can just write them an email. Some of them. Oh, okay. Sunwoo is going. Is it?
Uh,
No, I
I'm
think
going now.
It's actually
Okay. Bye.
Oh. Okay, okay. Ariana is going now. Bye. Bye. Have a nice day. Thanks for joining. Okay.
have a nice day.
Yeah, have a nice day. Yeah, so I think it helps to be a bit shameless sometimes. You just write an email, and if perhaps you can include some of your work, and if they see that you are advanced, which you are pretty advanced, then I think they'll be more likely to help you. Yeah, because I guess remember that most researchers, they were also like us when they were young. They were also very
Yeah.
passionate, so they're actually happy to see talents like you want to reach out to them. So
I also have this kind of idea where actually I have like as you can see Seung-Ju Hong is from our school, like he's an alumnus, I would say,
mm,
from uh a few years back, and
mm,
in the same year as Seung-Ju Hong, there's this person called Juni Kim who I mentioned earlier, and he's researching high energy physics, and
mm.
I know him very well, and he knows a professor very well. So I was
Oh,
wondering if I emailed that professor, who is also doing Hep DH, it might be a more advantage.
yeah, sure, sure. Wait, if you say you know the guy very well, then why not you ask him to email the like basically the guy will act as the bridge between you and the professor.
Yeah.
Yeah. So actually that's how I met my current mentor, because I worked with another mentor, and after I finished the project, I told him whether he could help me.
Ah.
So yeah, it's like it's sort of like a recommendation. You can ask your friend to recommend you, and that always helps, I guess.
Oh, okay.
It's like a
Okay.
referral. Yeah.
I think that
I
might work.
have a, okay, okay, I have a question about your presentation.
Sure, sure.
I was very interested in the Majorana representation and the Majorana and using the result to compute the very curvature and very curvature.
Mm.
And are there any multi-band generalizations to like four band, five band, or
Okay.
other more band? Are there any
Uh,
multi-band generalizations?
right now, yes, there could be generalizations. Right now, my paper is completely on the three band model, because for three band models, I already like it was tiring enough, so I'm stopping at three bands. But yes, you could entirely generalize, and in fact, actually, my research is based on there's one paper by another group, Liu and Fu, and they actually they analyzed berry phase of any band, so it's multi-band models also. Yeah,
Mhm.
so they analyzed berry phase, and in a sense, I I I I used one of their formulas, and I differentiated it to get the formula for berry curvature. So my research builds on theirs, and theirs works for multi-band, whereas mine is only for three bands. Yeah, but that's entirely possible to have um,
Oh.
more
Oh,
bands.
yeah. Uh, Actually, at this current moment, something amazing happened.
Mm,
Some younger students joined us. Yes.
yeah, hi.
Im Solho, it would be great if you could change your name to English letters because
Oh, no
people could
problem. It's fine.
pronounce it easier.
Uh,
So yeah. So here's Im Solho and Ban Jiho. They are
mm,
uh, very much interested in physics at our school, and Jiho Ban is currently writing a book on quantum mechanics,
oh, cool.
and the two of them are working hard to study stuff like general relativity, quantum field theory, etc., etc. And they're very, very young and gifted. As seen from the perspective of someone who is 2 years older. So yeah.
Yeah, nice to meet
Yes.
you. Hi. Do you guys
Hello,
want to-
everyone.
Hello.
Hello.
Yeah, it's great that you guys are interested in physics and quantum mechanics.
Oh, excuse me. I
Mhm.
didn't hear.
You want to say anything?
Oh, I'm in outside, so I can't hear well. Can you say one more time, please?
Okay, yeah, outside. I said, yeah, welcome, and yeah, we will be happy to help you in your studying as well.
Yes.
Good job, good job. Yeah,
Yes.
very cool.
I'm not, uh, I'm not very deep in this part, so I'm just learning. I'm amateur, so let's have a good day.
Yeah, you too, you too.
There's actually like an interesting anecdote about these students. Like it's actually something that has caused a bit of controversy at our school. Not much, but our school has like a physics club, and as physics clubs do, in order to select new members, there's like a test with problems that are made by people who are currently higher ups that are in the physics club. And I was asked to create one question, and I did it on the derivation of the Ryu-Takayanagi formula. Okay, so making that question, my initial thought was, okay, I'm pretty sure that nobody will be able to solve this, but I'm just gonna make this question for the possibility that one person will be able to solve it very well. And the result was that 2 students solved it excellently, and these 2 students are here today. Yes.
Oh wow,
Wow.
that's amazing.
Wait, by the way, can I ask what formula was that again? Derivation of what formula?
The Ryu-Takayanagi formula. I'll just write it in the chat. It's really famous like these days. As I have previously said, the derivation itself isn't that difficult if you assume ADS-CFT is true. So, but the result and the way of deriving it is actually very interesting, because there are a lot of relationships with other areas of physics, like statistical mechanics and stuff like that. The replica trick is a very powerful tool. Basically, you use the replica tool to calculate entanglement entropy, and what it means is that you take like the trace of the multiplication of n copies of the same density matrix. So like if you have a density matrix for the state, you send it to the nth power, take the trace, and then you analytically continue to real n and take the derivative at n equals 1, and then you get the entropy.
Oh,
so
cool. Oh, so there's some analytic continuation and complex analysis involved as well?
Actually, in the case of the Ryu-Takayanagi formula, in the case of general relativity, the function becomes a linear function of n. So you can quite easily take the derivative. I'll just write it down in the chat. Replica trick.
Replica trick. Very cool.
Yeah. And there's also some stuff about the Ricci scalar becoming a delta function at the tip of a cone. And so yeah, these kinds of interesting things all come together in the relatively simple derivation of the formula, which is really interesting. So yeah.
Cool.
In my opinion, it was a decent problem. Yes.
Perhaps one question. You guys at high school, you guys have some club where every year you have a few people like you, like-minded people. Oh wow, that's very
Yeah,
cool.
that's something I want to know as well. Cause wow, the fact that you set a problem like that sort of shows how high the standard is, which is I'm quite surprised really.
So I was wondering what kind of school you go to, like what
Oh,
type of school?
Our school is supposedly one of the top schools in this country, but like considering like but it's not, we don't really do a lot of, for example, out of school stuff. Like the most we have is, say, math and physics Olympiads, but we don't have stuff like, we don't have a lot of people like actually self-studying physics and math on their own, like self-studying university level stuff.
yeah.
Like even those who are into math Olympiad, right? They are only focused on math Olympiad. They don't know about university math, for example.
Yeah, most of the
I
time.
see.
So
yeah.
people like like it's somewhat rare for people to be studying things like quantum field theory. So
Yeah, it's very rare.
it's in a sense I'm a bit lonely.
Yeah, you know, like I'm pretty sure, like Ariana was in the call just now, right? I'm pretty sure she's probably like the only one of a
Person
kind
who-
in this entire country we have here. Like,
Yeah, he's really exceptional. Yeah.
Yeah. Our school is like kind of like defined differently. So like it's a science high school. So the official, like, how should I say this? Like the official curriculum has like elective courses, and these include university level mechanics, electrodynamics, quantum mechanics, but not including perturbation, and statistical mechanics. And then you have additional elective courses like many body quantum theory, general relativity, a bunch of other cool stuff. So yeah, I would say that our school is very math and physics oriented. All This is just like a rubric, I guess, but like all of the IMO participants of Korea for like the last 10 years have been from our school.
Oh, I see.
So yeah, the government clearly went their way to create a school for students gifted in physics and math, which really helps like create friendships, because there
The
are indeed,
atmosphere. Yeah.
there is indeed a high density of students who are interested in theoretical physics, still like not that much. I would say on average 1 to 2 students every year.
Oh, cool.
But the year that the year that Jiwoo Ban and Soho Lim are currently in is quite interesting, because based on what I've seen, there are like 5 to 6 students, 4 to 5 students who are incredibly interested in theoretical physics in that year alone. So that is like
That's
one
great.
of those golden years. Yeah.
I see.
A golden age for physics at our school. Yes.
Say from like the normal student like me, actually Jiwoo is still a very exceptional student, and most of the people who study like QFTs are actually kind of influenced from him.
Oh,
no, thank you. That is very flattering. Yes.
And I have another meeting soon, so I think I have to go. And it was really fun, and yeah, nice to talk with you guys.
Yeah. And by the way, Sunwoo Kim has this meeting where they all study QFT. Is that correct?
Yeah, it's kind of a study between some of the friends, but actually it's kind of became 2 people. Yeah.
Oh yeah. So it's like only 2 people at this point. So I guess anyone who participated in this chat could join, I guess.
Is it a QFT study group? Or?
Yeah, actually, there's a channel named channel by Tobias, and he has lots of videos like symplectic geometry and even conformal field theory.
Wow.
So, my goal was to study QFT and symplectic geometry, and then conformal field theory. So if you're interested, I think we may kind of do it together.
Oh, that's a cool channel. Yeah,
that's
oh,
neat.
that's a really cool channel. Sure. You can you can always contact me if you want to study together. Yeah.
Let's talk about it sometime. Yeah. Thanks.
Okay. I think
I have to go.
actually okay. Right. Yeah. Thank you. Bye. I think actually to be honest, I haven't eaten dinner. Do you guys want to do you guys have any more things to discuss, or do you guys want to call it the meeting?
Yeah, let's call it a day.
Okay.
Yeah, sure. So yeah, thanks everyone. This has been quite motivating.
Yeah, let's do this later on also. So like how often do you want to do these types of meetings? one every 2 weeks or like once a month, or once every week?
If you feel any specific things you want to share, you can always feel free to drop a message, perhaps once every 3 or 4 weeks. That seems like a comfortable amount, or once every 2 weeks.
Okay.
But if you have more things to share, I'll be happy to hear. It depends on how many things we have to talk about also. Yeah, so
Okay.
I'm very
That
free. I'm
sounds-
very
that
free.
sounds
So
good.
feel free to just drop by. Yeah, thanks everyone. It has been great meeting now.
Okay.
Thanks.
Bye.
Bye.
Good night.
That's fun.
Bye.